I was recently talking with a customer and they asked me about CDC and how it behaves in the event of an outage. And at the time, I didn't have a good answer for them because it's not something I tend to talk about. But in today's episode, we'll talk about how CockroachDB's built-in CDC change data capture behaves in the event of downtime. And by downtime, I'm talking about things like node failure, or maybe simply stopping a change feed by pausing it and then later resuming it. How does it behave under those kind of circumstances? CockroachDB's CDC is built atop CockroachDB's existing distributed jobs infrastructure. So as you can imagine, it's built to last and it's self-healing. We'll see all of this in the demo. And finally, it's subject to admission control. So if, for example, you pause a long-running change feed and millions of messages pile up, once resumed, the CDC job will continue, churn through those messages that it didn't publish in the time that it was paused, all without affecting foreground traffic. Let's take a look. I'll spin up a Docker environment, which has 3 CockroachDB nodes, a Kafka node, and a load balancer for CockroachDB. I'll initialize the cluster. I'll create a Kafka topic called purchase, and I'll connect to CockroachDB. I'll create a table to store purchase information. I'll pre-split the table into 16 ranges. This is just to simulate a table that's already been populated with data spread evenly across all ranges. I'll enable range feeds and then I'll create the change feed itself. So this is creating a change feed for the purchase table, and I'll be sending messages to a Kafka topic named purchase, flushing either when I reach 1,000 messages or 100 milliseconds has elapsed, whichever comes first. On error, I'll pause the change feed instead of failing it, and I won't perform an initial scan. This will only publish new messages. With that set up, I'll start an application which will write to the database and then subscribe for CDC events. And my infrastructure will look like this. There are the 3 nodes in our CockroachDB cluster. I have an application that will write to the database, and the database will publish a change feed notification to a Kafka topic, which I'm then listening on within the application itself. And then I can determine the latency between the point of write and the point of read. And that's what I'm displaying down here. And we can see that it's taking around 3.5 seconds for a row that I've just written to the database to be read back into the application via change feed. Pressing W toggles writes on and off, so I'll toggle those off and we'll see that we catch up. There are no unread messages. If I continue, we hover around the 100 unread messages mark, but never really going too far above 3.5 seconds. And with this query, we'll see that our change feed job is currently running and the coordinator for that job is node 1 or CockroachDB 0. Change feeds are running on multiple nodes wherever there are leaseholders for a range, but there'll be one coordinator node. I'll take down non-coordinator nodes and I'll take down the coordinator node just so you can see how CockroachDB behaves. First though, we'll pause the change feed job and we'll let the messages build up. So the latency will pause because we won't receive any notifications and the number of unread messages will build up. Now I'll resume the job and the number of unread messages will come down and the latency will spike because we wrote a message a little while ago and we're only now seeing it in the application. And now you can see we're batch sending the change feed notifications that we missed and the application is catching up and the latency is coming right back down again and it will hover again around 3.5 seconds. I'll stop writing now just so you can see that we will get down to 0 unread messages. So we haven't actually missed any messages at all. Coming over to the UI, if we have a look at the metrics, there's a dashboard for change feeds and we'll see that the commit latency spiked during the time that the change feed was paused. And there was a sudden rush of bytes being sent from the change feed in order to keep up. This would be a longer, shallower spike if the cluster were really busy and running on constrained resources. That would be admission control kicking in. But at the moment, the cluster isn't strained, so admission control doesn't need to kick in. And that's simply because when the change feed was paused, it stopped running on the original coordinator. And when it resumed, a new node took over the coordinator role. Let's take down the nodes now, starting with a non-coordinator node. So we're restarting the Docker image for the first node, and we'll see what impact that has on our workload. So we can see that messages are going unread. And what we're seeing here is the number of unread messages is going up because the CDC job for the leaseholder involving any ranges for that stopped node are being resumed. So we'll eventually come back down to a low latency with low unread numbers. And there we go. I'll stop writing for a minute. And we haven't missed any messages at all. We'll start messages again. So let's kill node 3 and take a look at the unread messages and latency. As with node 1, any change feed jobs that are running on the node that I killed for leaseholders on that node aren't currently writing, but will be resumed. So we've started writing again, and those messages will now start to come down. Running that query again, we can see that a new coordinator was elected, and there was a spike in emitted bytes from the change feed, just to catch up. I'll let it fully catch up, I'll stop writing, we'll check for 0 unread messages, and then we'll kill the last node. Back down to around 100 unread messages and 3.5 seconds of latency, I'll stop writing. We haven't missed any messages. And now we'll kill the last node, now directly killing the coordinator node. Keep an eye down here. Now the messages are going to pile up again, and very shortly the job will be restarted and it will get a new coordinator node. And we can tell when that happens because the latency will spike, indicating that we're starting to read again. Now we have a new coordinator node. Now it's node 3. The emitted bytes is spiking, indicating that we're now pushing through any messages that we missed. And that in turn will bring the unread messages back down to the 100 range. Taking a look at the latency, we can see that we're currently experiencing another latency spike. And that's simply because the application is aware that it wrote to the database around a minute ago, but because we took out a node, the change feed needs to ramp up again. And those messages are only now starting to arrive back into the application. I'll stop writing one more time. And we can see that throughout all of these tests, we didn't miss a single message. CockroachDB's built-in CDC is highly resilient to failure, and it self-heals in the event of failure, meaning that you and your team aren't woken up in the middle of the night to recreate or resume change feeds. As with a lot of our customers, you might have a very busy cluster with hundreds of thousands of change feeds being published every second. And for clusters like this, CDC with admission control can back-populate any messages that you may have missed during an outage without impacting foreground traffic. So the next time you create a CDC change feed, rest assured that CockroachDB's resilient distributed jobs engine has you covered.